Right. I think the previous presentation ended up here when we had managed to convert a number in rectangular form to polar form, and they later represented as exponential. I remember that this was just a number with modulus 1 in this way, and we ended up seeing that a number z can always be represented as a product of two numbers, a real number, which is absolute value of z, multiplied by e j theta, where theta is the argument of the number. You remember that, isn't it? Okay. So we're going to take from there today. We need this expression like this. And remember, we said we're going to use R to denote the absolute value of z. So now what we have here, we're going to take integer powers of complex numbers. In this case, we're going to discuss positive integer powers of complex numbers. Now, if I'm given a complex number, I want to see how to calculate something like this, z to the power n. Is that clear? Okay. So in that case, you're first of all going to consider n being a positive whole number or natural number. Then we do the CD calculation. Now, first of all, let's take z. We said z as in rectangular form. That is that one. Then we can go on and calculate r, which is x squared plus y squared. And then our theta, our argument of z, this is the argument of z, we normally write it this way, arg of z. And this is tan second function y over x. Then again here must remember how if your coordinates are in the fourth or third quadrant, how you determine the angle using the reference angle. Is that right? So now, at the end of a good discussion, you've got z represented this way in flower form, represented as r e to the power j theta. Is that right? Okay. Now, if we're to take this z to the power n, check that. It will mean that we're taking x plus jy to the power n. But let's say n was 9, and with a number like 3 plus 4j, and you elevate this number to power 9. You'd have 9 factors of this, isn't it? I think you can see already, or can feel it, that this is going to be tedious. Somewhere I think you're going to have 4 to the power 9, j to the power 9, and a lot of j to the power 8 and whatever, somewhere in between, isn't it? So this is kind of tedious to do this thing this way. So what is the more convenient way to do it? Is to represent the number this way. You see that? So now what do you do then? You take the number this way, and say to the power n. I'm going to advise you there. If I see you having, let's say, even 3 factors here, or 4 factors here, you write 4 factors like this to multiply that thing. I'll just take you that you don't understand what we're talking about now. Because that's going to be very, very tedious to do that. So the best way to do it in exponential form like this. Now, what are we having now for this? We have the fact that x y to the power n is equal to x to the power n y to the power n. Is it? Those are rules of exponents. Is it? We also have that x to the power a to the power b. This is what? X to the power ab. All together. By doing this thing, I'm also trying to pass a message there that, guys, when you're doing this, you must always refer back to things which you know and use them in a situation which is given there. Are you together? Okay, so what we do now here, we're going to have here r to the power n and the e to the power j theta to the power n. First, this operation, we're applying this first part. Now, in the next operation, now we've got a to the power x, where our x is what is e. Then we're going to apply that. Then we come here and say this is r to the power n multiplied by e to the power j n, to the power j n theta. All together. Now let's look at this. This z to the power n is now equals to r to the power n. Notice that this is a real number. R is a positive real number. To the power n, we've got a positive real number there. Then we've got e j n theta. Now remember, when we started discussing numbers in exponential form, we had e to the power j theta, isn't it? What was it equal to? What was it equal to? I've just showed you here. There. We've just forgotten it. Do you see it or don't see it? Do you see it? So you need to apply this. This is e j theta equals to cos theta plus j sin theta. Is it? So now coming to this situation here, our theta is not just a simple theta, but a multiple of theta, n theta. So we got to have this thing as r to the power n brackets cos n theta plus sine, there's j sine n theta. Maybe we need brackets here to avoid that repetition of sign that could confuse. Then that's that. That's a formula for elevating a number to the power n. And this has got a meaning. Look at what's happening here. Look at what's happening here. It tells you that if we had an angle like there, let's say 45 degrees, you elevate that thing to power 2, what's going to happen to the angle? It's going to double. Do you see that? What is going to happen to the magnitude? It's going to be squared. Altogether, if this is 1 and 1, that's the square root of 2. So when you square it, it's going to be 2. Now, if you elevate to power 3, this will be multiplied by 3, the angle, the argument, going to multiply by 3. Then this one will be elevated to power 3. So you see what's happening there? The modulus of the number, as we elevate it to a certain to positive powers, the modulus increases. What about the angle? The angle also increases. It's like that arm, the vector, is being pushed around the what? The origin, rotating. So actually, that means somehow elevating a number are to successive powers of n. It's like rotating the vector around the origin, but at the same time rotating it, you are increasing what? The magnitude, depending whether this r is more than 1 or not. But if it's less than 1, what's going to happen? Elevating a number to power n, which is less than 1, the magnitude is going to decrease. So the vector is going to be smaller and smaller rotating, but smaller and smaller in magnitude. Are you understand what I'm saying? So let's take, like, you've got the vector there. You elevate your power, the angle doubles. It will point this way, but it's going to increase the magnitude. You elevate to another power, the angle is multiplied by 3, but increase the magnitude. So it's going to be a vector which is going like increasing the magnitude, rotating around the origin like that. Altogether, each time you increase the n, this is what's going to happen. Do you feel it? Do you see it from this formula? Okay, so that's elevating complex number to powers of n. Any question at that point? Now, we've got examples there, some numbers to look at. Let's take one example and see whether we can do that. Let's take, maybe let's get some space here. Okay, what number? Just take Z1. Z1 Z1 is equals to 1 plus J square root of 3. So first of all, the absolute value of Z1 will be the square root of 1 squared plus square root of 3 all squared. That's going to give us 3 plus that is 4. Then we get our square root of 4, which is equal to 2. Then the next thing will determine the argument of this number. So we say theta equals to arg z. Guys, there's no rule here which says I should start with the modulus of that. But in this case, you can say this is our initial step, and this is our second step. Then here, this is second function of tan square root of 3 over 1. What angle is that? That's a special angle, isn't it? What angle is that? Sorry? 60. In radians? In radians is pi over 3. Let's just use it that way, it's pi over 3. There's no need really to go to decimal numbers unnecessarily. Is that right? So it's pi over 3. Then the last thing maybe what we can do here is to represent our number in what? In exponential form. So we've got Z1 equals to 1 plus J square root of 3, which is equals to 2 EJ pi over 3. Now, if we take, let's say, first of all, we say Z1 to the power 2. If we follow this formula, this Z1 to the power 2, it will say 2 to the power 2. Then this side we're going to have E J pi over 3 to the power 2. Then we do that, we get 4. And then here you're going to get 2 pi divided by 3, which is a bigger angle than this one. Is that right? So we are going to have here now E J 2 pi divided by 3. So now if that vector was pointing somewhere there, what has happened here? That angle has been multiplied by 2. So it has to double this angle, so it's going to go that side. And the modulus has gone up to 4, so it's going to increase more or less to 4 altogether. So that's what's happened. So what happened? The vector is rotated, moved, displaced to in positive direction by double that angle. Are we seeing that? Okay. So now, can you try to do on your own? Let's try to do Z2. Notice the steps. Notice what you need. You need the number. In this case, let's get Z2. Let me give you power for Z2. Let's have Z2 to the power 5. Calculate Z2 to the power 5. So I wrote Z1 here. Should be Z2. So when I'm saying master, you must master this work. You must know exactly what do you need. I don't want to see you writing clumsy 5 factors of this number in rectangular form and trying to multiply. That will take you maybe quarter of an hour or so. The new number, this number we're giving you Z2 is this one. You didn't see it? What are you looking at, my friend? Z2 is on the board. What do you mean by no, sir? You should have said you don't see clearly, but not if you don't say you take the, I say Z1, you give a number, I say Z2, you take the same number. Then there's something seriously wrong. Hey. I said when you're writing numbers in exponential form, I don't know whether I told you that, but I think I told you. In exponential form, strictly radians. The number we're working with is Z. Z1, this Z2, ne? Z2 equals to Z2 equals to 1 plus J, and then the modulus of Z2 is equal to 1 squared plus 1 squared, isn't it? Which is square root of 2. And the angle is obvious. What is the angle? Yeah, but we're working in radians here. Pi over 4. So now this number is square root of 2 e pi over 4. We say to the power 5. Power 5. So now Z2 to the power 5 is equals to square root of 2 multiplied by e. Oh, sorry, there's a j missing here. Do you see that? Okay, must correct that. It's j over 4, all that to the power 5. So you can simplify your power 5 here, apply it to 2. It will be square root of 2 squared, square root of 2 squared multiplied by square root of 2. Then that side will be e j 5 pi over 4. This gives you 2, then you get 2 square root of 2, isn't it? No, 4. 4 square root of 2. Then we got 4 square root of 2 that now notice when you get to this point here, I can ask questions like additional questions like give your answer in what? In rectangular form. So we've got to go over that those trigonometric ratios of 5 over pi. Isn't it? Cos 5 over pi over 4 plus j sine pi over 4. Then you calculate the numbers, you get your number in rectangular form. Or I can say give it in modulus argument form. Modulus argument form is that form when you get this, you've got the modulus, then you've got the argument there. Then what do? You just drop e and the j, then you just take these two, you put it in this form. You must master that also. Is that right? Okay. So I think I'm going to move on there. I'm going to leave this thing for you to practice now. Right. Let's come to the next. The next discussion is on roots or rational powers of complex numbers. Now we're computing nth root, like square roots, cube roots, fourth root. Now what I'm going to do here, that set, given as it is, we know we can compute R, that is not news now. Then we can compute the modular, the argument. Then you can write this thing as J theta. Now, I need your attention now. You must pay serious attention now. Let's suppose I've got a vector there. Do you understand that? Can you stop writing and pay attention to this? I've got a vector then. And they say this vector is representing this number I've got. Tell me whether this equality is valid or not valid. Say correct or tell me that no, this is wrong. Think about this. This is the vector. I take the vector, I rotate it 2 pi. Is it going to be there? You take a vector, say theta, there is theta. You say to theta plus 2 pi. Am I going to blend back here? Some people they don't seem to know what is 2 pi. There is theta. There is theta. To theta, I add an angle of 2 pi. There is theta plus 2 pi. That is my 0. That's my 0 plus 2 pi. Pi 2 pi. So is this and this equal? Is this equality valid? I'm asking. Is this representing the same vector or not? Come again? It's same vector. Exactly. The same vector. Even if I said minus 2 pi. Let's say I put here minus 2 pi. So I can go clockwise pi 2 pi. Is this the same vector? So this number and this number is exactly the same number. What am I trying to suggest there? I'm suggesting that even this one, R, E, J, theta, plus or minus 2k pi. As long as I'm taking even multiples of pi, I'm getting the same number. So because now what I can do, I can take, okay, this is 0. 1, 2, 3, 4, 5, 6, pi. The same thing, isn't it? Or I take it the other way around. Pi, 2 pi, that's minus 2 pi. Minus 3 pi, minus 4 pi, just like that. As long as I take in that form, that is exactly the same number. Am I making sense? Do you see it? Okay. So now let's discuss now computing a rational square root. Sorry, a rational power of this. A rational power of this would be something like this: z to the power of n. Then that will mean that I'm taking r e to the power j plus or minus 2k pi that, and I'm taking that to the power 1 over n. Then 1 over that, simplifying this, I think you can see that this would give us r to the power 1 over n, which is the nth root of a real number, which is not a problem because the modulus is a real number, isn't it? Then when you come this side, this is going to be e j theta plus or minus 2k pi all to the power 1 over n. Simplifying that, you get r to the power 1 over n multiplied by e j theta plus minus 2k pi divided by n. You understand what I'm saying? Divided by n. Now, check. Now, these are no longer going to be multiples of 2k pi. If I divide here, what I'm going to be adding here is not going to give me the same number. If for example, if k is 0, I'm going to have the first angle divided by n. So if it was 60 and this n is 2, the new angle will be 30. It's not that same number which you started with. If I take 2, I've got 2 pi here, added to the angle, divided by, so if I take k2, I'll have 2 pi here, added to the angle, divided by this root. It will be a different angle. So what this suggests actually, that these answers here, I will have to number them in terms of k. Now I'll choose here to write them in a modulus argument form. If I write this number in modulus argument form, look at what I'm going to do. I'm going to write the modulus here as 1 as r to the power 1 over n. Angle, this is how we read this thing. We say r modulus angle, we take the angle, only the angle without j. This will be theta plus 2k pi over n. Let's work with the plus only because we know that even if we work with the minus pi, or we just take on to get a different number, isn't it? So now, what is this k now? K is going to run from 0, 1, 2, up to n minus 1. This is very important what I'm saying here now. It's a fact which you must know always. If I've got an equation, z to the power n equals to a complex number z0, we must know that this equation, when you solve it, we must get n solutions. You know that, isn't it? So, like a quadratic equation, it's got power 2. The highest power we are known is 2. The equation has got what? 2 solutions. A linear equation, the highest power in the linear equation is 1. The equation has got 1 solution, isn't it? So now what's going to happen here? We're going to count all this 1, 1, 2, up to n minus 1. Plus this one. So they are n roots. So which means here I'm going to get I'm going to get n different numbers as nth roots of what? Of z. Am I making myself clear? Okay. So now, I think now what is important now is to take a number, an example, and use it to work with this. All together? Okay, let's come to this point here. Now this is actually an equation. Z cubed minus 1 equals to 0. Solve that. What's going to happen here? We're saying Z cubed minus 1 equals to 0. Then which means Z cubed equals to 1. Remember 1 is a complex number. This is 1 plus 0 j. Now to do what we're doing there, to get the three roots of 1, we need this formula. We need the modulus of 1. In this case, I'm just going to say modulus of z. And then we need the argument of 1 plus 2k pi. That will be divided by 3. Now, k is going to be what? Can you tell me what k is going to be? K, I talked about k before. What is k? Come again? Guys, give me k. 0, 1, and 2. That is 3 minus 1. So we're going to have 3 solutions. Now, when this come here, this number in this, as in exponential form, this number, the modulus is going to be 1, and the angle is 0, because the 1 is on the x-axis. The angle between the x-axis and the vector 1 there, that complex number is a vector, is 0. So it's going to be e to the power 0 j. Actually, when we get to this, it almost looks more nonsensical than anything, because now e to the power 0 is 1. It looks like we're moving in circles. There's 1. But for the purposes of calculating square root, you need to come to this formula. So now what I'm going to have here, I'm going to have z k equals to 1, 0, the argument of 1, plus 2 k pi all over 3. All together. Now let's start. Let's get z0. When we're getting z0, it all means that we must substitute k there by 0. This is z0. K is there. K is there. So by 0, isn't it? So we're going to have 0 plus 0, which is 0. Then we've got 1 here. Argument 0 over 3. Then we'll do that. We're getting exactly 1 e to the power 0 j, which is actually 1. And it's true. 1 to the power 3 is 1. Let's come to z1. Let's come to z1. Z1 will be equals to 1. Now k is 1. Then we're going to have 2 pi there. Then I've got 2 pi over 3. Then we need to write this in rectangular form. This would be what? 1 times cos 2 pi over 3 plus j sine 2 pi over 3. Can you find out what is it? What number is this? No, I don't think so. Negative 0.5 minus 1 over 2. And this one, I think is square root of 3 over 2, because this is a special angle. All together? Right. Then let's take, let's calculate Z2 now, the third root. As you're calculating Z2, I would invite you to think about the argument of a complex number. Just think what an argument of complex number is. Then what I'm going to have here, I'm going to have one angle. What is that? K is 2. Then I'm going to have 4 over 3. Then we're going to have cosine 4 pi over 3 plus j sine 4 pi over 3. Can you tell me what you're getting there? Do your calculations and tell me what you get. But I said, as you're calculating that value, you must think of the conjugate of a complex number. You are getting minus half. Yes. Minus j square root of 3 over 2. If you just minus the square root of 3 over 2, you're going to get a real number. Be careful there, isn't it? Okay. So now what do you think about these two numbers? Nothing. Are these two numbers related? What are they? They are conjugates. They are conjugates, isn't it? Now, this is a fact of life. Always, when you get one complex number as a root of another complex number, then the conjugate is also a solution. So a complex number cannot be a solution to an equation when its conjugate is not a solution. Always they go in pairs. Altogether, they always go in pairs. A number and its conjugate, a number and its conjugate. I wish you could write that down, because that's something which is going to be useful along the way as you proceed with your mathematics. A number, a complex number, and its conjugate are always a root to. They come as roots, paired roots to a equation which involves complex unknowns. So once you calculate one, once you've got experience, you calculate one. You can just calculate one, you determine the other by just calling upon the conjugate. You calculate this one, you get, in other words, you get 2 for the price of 1. Like Deponent sells pizza. Is that right? Okay, so that is important. Now, I think what you can do again, you can check these numbers. Absolute value of Z1, absolute value of Z0, absolute value of Z2. Let's use the absolute value of Z2 here. It will be square root of minus half squared plus square root of 3 over 2 squared. I think you can see that gives you 1/4 plus 3 quarters, which ends up being 4 quarters, which is 1, square root 1. So the 3 numbers, they have the same modulus. All together. Now, on this Argand diagram, check this. Check this. On this second diagram, 1 will lie somewhere there. Then if you look at this one, if this was pi over 3, you said it's 60, isn't it? Then times 2 is 120. So that vector will point more or less like this. The other one, 3, it will point more or less. What I can tell you, which is not visible now here because this is a rough sketch, these vertices, these points here, the complex numbers we're talking about here, they will actually form an equilateral triangle around the origin. If it was root 4, you will have 4 points. They will form a regular polygon around the origin. If it was 5, you get a regular pentagon around the origin. Conclusion: the roots, the n root of a complex number are vertices of a regular polygon of n sides. You are calculating root n. You get the roots, individual roots. Those roots, they form vertices of a regular polygon of n sides. That's also a fact which you must know. So what I want you to do now, I want you to do as a homework, I want you to do this one and plot it on the system of coordinates. Plot that on system of coordinates. This one also do the same thing, so that you can feel this thing I'm talking about. This one is 5, so you must plot a pentagon which has got its vertices on the roots of this number. Am I making myself clear, guys? Okay. So please don't make a mistake, because then I'm going later to check whether you can do these things. When I'm saying I'm evaluating you on these things, I'm precisely checking whether you can do, you know these things, and you know how to calculate computers. First of all, you must know that the roots, the n roots of a complex number are vertices of a regular polygon. So now when you calculate them and say present them, you must know how to calculate them, you must know how to represent them on the Argand diagram. Am I making myself clear? Okay, any questions? No questions. I hope you understand. Now, let's come to this one. I think this is almost the last part one. Anyway, we're coming to computing logarithms of complex numbers. I think I promised you last week that for the first time you are going to see the logarithm of -1. Did I tell you that? I didn't. Maybe I mentioned that group. Today you are going to experience for the first time maybe the logarithm of -1. But you know that this cannot be calculated by a calculator, is it? Yeah. So it can only be calculated by human beings. Okay. So what's going to happen here? First of all, let me explain some terms we're going to use here. When I'm calculating logarithm of a complex number, I will use this notation. This is capital letter L, that. Then I call that logarithm of Z. Now, remember, this Z can be represented in an exponential form, is it? So this Z, I can write it, this is equals to logarithm, capital letter again, logarithm of R e to the power j brackets theta plus 2k pi. What we've learned from the previous slide is that a complex number has got infinite arguments. You understand what I'm saying? You don't understand? Don't you see that when you get this k, you get a different angle? What is it? It's an argument of that complex number. If I change k, how many k's are there? Maybe I didn't mention it there clearly, but k is an integer, negative or positive. So how many integers are there? Come on, can you count them? Yes, you can count them. But can you exhaust them? You cannot. Then we say they're infinite, isn't it? So if the k's are infinity, which means these kind of arguments like this, they're also infinite. So a complex number has got infinite arguments. The one we calculate using those coordinates is one of them. Where to get the others? Just add 2 pi, 2 pi, 2 pi minus 2 pi minus 2 pi. You get the same number. I illustrated that on the system of coordinates, isn't it? Yeah. So get it sinking in your head there in your system. A complex number has got infinite arguments. Now when this is where it comes this zeta. Pay attention. This is where comes this L here, capital letter Ln, because logarithm of z is not a number. It's infinite numbers. Because now what I'm going to get here, I'm going to get this as ln r. Why can I use ln here? Because this is a positive number, it's a real number, I can calculate its usual ln altogether. Plus, this is a complex number, and that is infinite numbers. I'm going to write it like this. But the rules of exponents, they still apply here. Sorry, the rules of logarithm, they still apply here. So what I'm going to do now, I'm going to say now ln plus j theta plus 2 k pi in brackets multiplied by ln e. And here I can maybe change it to more letter e, but it doesn't matter. I put that. But ln, this ln is a base e of e. That's one, isn't it? So then we get here ln plus j theta plus 2 k pi. So guys, from this point, you must see that this is not one number. Altogether, it's infinite numbers. And then that kind of logarithm we use what? This capital letter there. Altogether? Okay. Now, are we always going to ask you to calculate the infinite logarithms of a complex number? The answer is no. It's like when we're doing with the trigonometric equations. We never ask you to give. We can say, okay, give the general expression of the solution, but sometimes we restrict you to a certain domain that calculate the solution within this domain from 0 to 2 pi or from 0 to pi, whichever the case might be. Altogether. So, but here we're going to talk of what we call principal logarithm. Now, principal logarithm is a unique number. This is no longer a set of infinite numbers, it's a unique number. Then what are we going to do? This is what to do. First of all, to calculate principal logarithm, you must also know what is called the principal argument. Let's say theta 0, principal argument. What is principal argument? Principal argument is an argument between minus pi and pi. Sorry, I need to correct something here. Between pi, strictly greater than pi, minus pi, less or equal to pi. What do I mean by that? If I've got a number, let's give a sketch of a first quadrant here. If I've got a number like here, check this. If I've got a number and this argument is that argument is principal. Why? It's less than pi. Because pi would go all the way, according to what is said here, it's inclusive there. But in this direction, it will go this way. It will not touch. That is in this direction. That is in the positive direction, and this is in the negative direction. So the arm of the vector must lie between that up to there. It mustn't go beyond pi, or lie this way. It mustn't go beyond minus pi. Am I making myself clear? So once you've got the principal argument, as your theta 0 there, then what can you do now? You can take your z, write it as r e j theta 0. Then now when you get the logarithm here now, you can now even use this small letter, ln z equals to ln of r plus j theta. I hope I'm not too fast today. I'm not too fast, is it? Okay, so that's the case. That's the thing. Now let's come to our big friend minus 1, which when we put on the calculator tells us nonsense. What is minus 1? There is z is equal to minus 1 plus j that. Let's get the parameters which you want. We want the modulus. The modulus is 1, because that is actually the modulus of minus 1. The argument of minus 1, where is minus 1? Minus 1 is somewhere there. Is that true? We'll be lying there as minus 1. What's the angle between that minus 1 and the positive x-axis? Is half pi and pi. So it's included here, isn't it? So then the argument here is pi. Then after that now, minus 1 is equals to 1 e j pi, which is the same as just e j pi. Now the logarithm of minus 1 as a complex number will now be equals to ln e j pi. Applying rules of logarithms, this is j pi. Are we together? Do you see that? What is that? J pi is a number, is a imaginary number which is lying along the y-axis just after 3j there. Then you've got the j pi. Are we there, guys? And this is a very beautiful kind of phenomena. This is very, very beautiful. Let me just show you some funny things about this, or some interesting things about this. Let's go back to the line, this one, where this is a set of numbers. Let's go back to this one, where this is a set of numbers. This will be equals to J. No, sorry. Let me write it correctly. The argument of -1 is what? Is pi, isn't it? Are you sure? The argument of -1 is pi. Do you agree? So, which means -1 will be the same as 1 e j pi plus 2k pi. You agree with that, isn't it? Do you agree? Now, if you come and calculate the logarithm will be j brackets pi plus 2k pi. That is as a set of numbers. Now, let's start at k equals to 0. Let's start here at k equals to 0. Let's say k equals to 0. What are we going to get here? We're going to get j pi. So if we do that, let's represent that thing. Oh, sorry. Let me check this. Let me put this thing this way. Let's take that to be a line, a system of coordinates, isn't it? Then let's take another one and put it this way. Just roughly. Now, if we were to talk about this number, and then think of a line y equals to pi, what kind of a line is that? Y is equal to pi. Is it a horizontal line, vertical line, and oblique line? What is it? Sorry? Vertical. Then here we start the problem. Now, when you don't know anything from metric, what is the line y equals to 2? Can you draw that line on the system? It's horizontal. So why should be y vertical? Y is equal to pi. Why should be vertical? That's a problem. That's a problem. It actually shows me that you have switched off from all the mathematics you know. You now want to know this new mathematics in Maths 1. There's no new mathematics in Maths 1. That mathematics we still use it. Are we together? Okay. Guys, no. This is bad, ne? Now if you think of that line, y equals to pi, let's just take a new scale here and say this is pi. If you think of line y is equal to pi as a line, that line is like this. Let me pick it and put it exactly at pi. There it is. That is pi. Do you agree? That is for k equals to 0. Let's talk about k equals to plus or minus 1. What are we going to do here? Let's take 1 first of all. Let's take 1. We are going to get 2 pi here, and plus that 3 pi. So we're going to get j equals to 3 pi. Now if you think of the line y is equal to 3 pi, what are we talking about? We're talking about this line being repeated there and there. Now it's 1, 2, 3 pi, isn't it? So then that line, we can represent it that way. Do you agree? Let's think of minus 1. Let's think of minus 1. We put minus 1 here. We're going to get minus 2 plus 1. What are we going to get? We're going to get minus 2 plus 1 pi. What are we going to get? Minus pi. So we're going to get j. Then if you think of the line y is equal to minus pi, then you're taking that measurement and you're putting it there. Then you are taking a line you are putting it there. Let's go for the last time now. Let's think of k equals to plus or minus 2. If you put 2, you're going to get 4, there 5. You're going to get 5 j pi. If you go back there, you're going to get 1, 2, 3, 4, 5 pi. Then if you think of that line passing there, y is equal to 5 pi, you're going to get, no. Let's get a thinner line. We're going to get a line which goes this way. Let's move it to the exact position. There. That was for plus 2, isn't it? Let's take minus 2. That will be minus 4 pi plus that will be minus 3. So get here, we've got minus 3 j pi. Then we come here, count 1, 2, 3. Then you think of that line which goes there, and then let's think of this. What do you think this thing is doing? For me, this logarithm is dividing the plane into stripes. Stripes. Do you see it? You don't see it? Then, if you are really guys clued up with programming and whatever, this plane here could be a kind of a sheet of textile clothing. That one is stripe. You can see your sheet is called stripe, isn't it? So now what do you want to do? You need to program a machine which is going to go, put a pattern here, take the other pattern, same pattern, there, another pattern there. Then go there, pattern there, go, a pattern this side. What do you have in there? You are producing a striped t-shirt. Isn't that beautiful? If you don't see the beauty, it's not a problem. You just don't have the eyes to see the beauty. But there is the thing. Isn't it nice? It looks nice to me. But anyway, what looks nice to me doesn't necessarily need to look nice to somebody. We agree on that one. But that is one of the things which you can, which is a good application of these logarithms in those kind of things. You actually see things happen like machine. You can see machine then go somewhere. So the cloth is rolling. It's getting stripes, different patterns, maybe no pattern, just colors stripe. Then you go around now putting a Kaizer Chiefs striped t-shirt. You think it came from Kaizer Chiefs. No. It's for Kaizer Chiefs, but it was made with the use of mathematics. All together. Thank you for listening. I hope you enjoyed it. If you didn't enjoy it, it wasn't my intention.